Okay, here is the Coriolis effect. Uh, Similar thing here. We're going to look at the most basic, and then we're going to look at a bit more wordy. Okay, so we have the Earth rotating eastward. The atmosphere rotates around with the Earth, so it's always moving in an easterly direction. The magnitude of this motion is greatest at the equator because the air has the farthest to travel, so that's what gives it that faster velocity near the equator. The eastward velocity decreases gradually towards the poles, and this variable eastward flow toward the north or south pole results in polar flowing air that deflects to the east in the northern hemisphere and to the west in the southern hemisphere. Okay, so remember, um, the best thing to do is uh, remember what type of rotation is associated with um, high and low pressure systems in the northern hemisphere, because that's where we're at. And then just remember it's the opposite in the southern hemisphere, and work it out then, because um, when you try and remember both, at least for me, you may have no problem with this at all, but for me, when I am attaching too many terms that are very similar, I get a little confused. So um, just remember one and then reverse it for the opposite. Okay, so here is the more wordy version there. So north of the equator, the air appears to move to the right from any point of view. So this is kind of cool, because if you place yourself at the end of any of these yellow arrows in the northern hemisphere, everything appears to deflect to the right. Okay, if you get at the bottom of the arrow and look in the direction of movement, it always appears to be deflecting to the right. And it's the same but opposite in the southern hemisphere. So south of the equator, air appears to move to the left from any point of view. So again, take a look at the end of the arrow, and it's always moving to the left. Either way you go. It's pretty cool. And all of this information we've just gone over already, but I wanted to give it to you in text this time because I know this can get a little bit tricky. The brain, you need it to cool. So, for the next slide, your notes say, describe how wind transports sediment and other materials. So we've got three main ways that sediment is transported by wind. There's rolling, bouncing, which is also called saltation, and there is suspension. Most materials on Earth's surface are too heavy or too attached to the surface for the wind to move them. Sand grains can be picked up by strong winds, as we here in Phoenix all know, who have made the mistake of going outside in a strong gust of wind, or worse, a dust storm. The grain is launched and then falls back down, sometimes skipping along the ground in a process called saltation. So if you think of the sediment, almost, it's like they're playing leapfrog. One bounces up and hits another. That one bounces up and hits another, bounces up and hits another. That's saltation. And then for the much smaller material, finer sediments such as dust, silt, and salt can be suspended in flowing air, meaning wind, and can travel thousands of kilometers. So these dust storms that we get here can travel a huge distance. What are dust storms and whirlwinds? So this image here is of North Africa. There's a massive sandstorm blowing sand and dust west of the deserts of North Africa. It travels 1,600 kilometers into the Atlantic Ocean. So this is enormous. Here in the Southwest, in desert settings, we get dust storms pretty frequently. They're common around thunderstorms. So as the wind picks up in front of a thunderstorm, we tend to get a dust storm. So, what are dust storms? Dust storms are strong winds that pick up large amounts of dust, forming a cloud that travels across the surface. And if you click on that link, you'll get a video of it. In contrast, whirlwinds, or what we often call dust devils, are much smaller scale versions. They're rapidly rotating air carrying fine sediment. So again, whirlwinds are just dust devils, and they're much smaller. They look like the little tornadoes of dust, like the Tasmanian Devil cartoons, right? You've probably all seen them here around Phoenix. Where is wind-blown sediment deposited? Wind-blown sediment creates sand dunes and finer-grained loess. So LOESS, a loess deposit. So the images that I have here, we have complex sand dunes in Great Sand Dunes, Colorado, that's pictured on the left. And dunes are near and dear to my heart. I'm from Yuma, and so it's right by Glamis, right by those big sand dunes. So if you've ever driven to San Diego, you've probably driven through Yuma and driven through those sand dunes, and they're so cool to just stop and watch how much sand can be moved around just by the wind. It's amazing. And so these dunes change shape every day. If you take a picture and then come back the next day, it looks different because the wind has moved it around. If you place a road right next to sand dunes, over years, or if you place your house next to the sand dunes, over years, if the wind is blowing your direction, the sand will just gobble up your house. It'll just be buried under what is basically a mountain of sand. And so when you look at them from the road, sometimes they look pretty small, or you think, oh wow, that's really pretty, I'm going to go climb up that. They're so hard to climb because the sand just keeps moving under your feet, and they are much larger than they appear. But the image on the lower right here is wind-blown silt. That's what this fine-grained loess is. And this is from melted Ice Age glaciers, and this image is from Illinois. So basically the glaciers go over a surface and just pulverize it into a tiny grain size, just this very fine dust, and then it gets picked up and moved potentially over 1,000 kilometers just by the wind blowing it around. It's pretty cool. Why does it rain or snow? We're going to start talking about the hydrologic cycle now, so the water cycle, and the two main things that we're going to deal with are evaporation and condensation. Evaporation occurs as water molecules escape as gas, vapor, from liquid water. Evaporation from the ocean surface is the primary contributor to water vapor in the atmosphere because there's so much surface area to the ocean. So evaporation will occur if you leave a glass of water out. It'll occur in a river or your pool, but most evaporation occurs on the ocean. Condensation is just the opposite. So evaporation, we've got liquid moving to a vapor, and condensation, we've got a vapor moving to a liquid, okay, or a solid in the case of snow. So condensation is where water vapor molecules cool and combine to form clouds and precipitation. So when we're talking about evaporation and condensation, we're talking about changes between the different phases of water. So how does the temperature of the air affect the phase of water? Well, if we take a look at this graph, we want to look at both axes and see what's going on. We've got the three phases of water, ice, liquid, and vapor, that can exist together at Earth's present-day temperature. So that may have been different in the past. It's different on other planets, but here, this is what we've got. Um, the red arrows indicate that the air heats up, passing from one state to another. The blue arrows indicate that the air is cooled, or rather, that heat is extracted from the air to allow the change of state to occur. So what phase occurs when the water is at 30 degrees C and 0.5 ATM, which is atmospheres? We take a look at our 0.5 atmospheres and take a look at about 30 degrees C, and we're looking at a liquid state. Okay, so we've got liquid water at 30 degrees C and 0.5 ATM, and you should be able to do this on your own on the quiz. So locate which of these three phases you're looking at for particular temperatures and pressure, which is represented in atmospheres. There's a little video here you can click on to watch. It's short, and if you've got kids, your kids might like it. So it is kind of silly, but it really gets the point across, and if you have a little laugh, that's always a plus too. So I highly recommend you click on this video and watch for some more information on the water cycle. So here is our more complex, realistic version of the hydrologic cycle. We have sunlight that liberates the vapor from liquid water, so triggering evaporation. Prevailing winds carry the vapor-rich air onshore. The air is forced to climb over topographic highs where the atmospheric pressure is reduced, forcing the air to cool. Vapor precipitates to liquid water and falls as rain. The windward side of the mountain receives most of this rain. So the side facing the wind, facing the ocean in this case, receives most of the rain, and the opposite side gets less rain, creating what's called a rain shadow desert. So the side facing the wind gets all the rain, and then the clouds are gone, the moisture's gone, so the opposite side is very dry, very arid. So what provides the heat necessary for the hydrologic cycle? The sun. What happens when warm and moist air rises into the upper atmosphere? It cools, right? As it cools, it condenses. So it's condensing into raindrops or ice crystals. What type of pressure system is associated with air rising? So if you're lifting that air up off of the surface, you're decreasing the pressure on the Earth's surface, which means you have a low pressure system. And what type of pressure system is associated with bad weather? Right? When we have storms, that's associated with a low pressure system because we need that warm, moist air rising up so that it can cool and condense and produce the clouds, produce the storms. So it's all linked together.